All right, today we're going to be looking at 3.6 derivatives as rates of change. I'm going to start out by going to the textbook and just pointing out a few definitions and terms that we want to be familiar with. All right, so it goes into describing a derivative as a rate of change. This is a position function, and it shows you the displacement where it moves, and we find the distance or the slope between 2 points. And so that's what we're seeing here, the average velocity. This is what we call the slope formula. The difference quotient is something that you might have seen this called by, but it's basically using the slope, change in y over time over the change in x or the change in time. This is average velocity. It's basically telling you the slope of a secant line that passes through 2 points. And then the instantaneous velocity is when we take the limit of the average velocity, changing the distance between those points closer and closer until they're right almost on top of each other. The change is 0, and the limit as that change goes to 0 is what we call the derivative, and it is the instantaneous velocity. Here is the more formal definition, and again it's telling you we have some position function, and as this object moves along some line, some curve, some path, we can find the slope or the average velocity between those 2 points using this formula. And then instantaneous velocity is the slope of the tangent line to a curve, which is just the limit of that velocity equation. You got some examples that kind of walk you through it. Down here, important speed and acceleration. When we only want the magnitude, so that is how fast something is going, we're not really concerned with the direction. We just want to know the speed or how fast it's going. We say we use speed, which is the absolute value of velocity. So you could have a negative velocity, and if you just take the absolute value of that, that will give you what the speed that object is at that point in time. Here we make a connection, and this is probably like one of the last big things I want to point out. We make a connection. It says because velocity is the derivative of position function, acceleration is the second derivative of the position function, and therefore if you want the acceleration, you just take the derivative of the velocity function, which is the second derivative of the position function. And then here is a diagram kind of relating those. So you have a position function, the velocity is the first derivative, the speed is the absolute value of the first derivative, and the acceleration is the second derivative. And then you have some examples and problems that walk you through finding velocity and acceleration. You will be asked to graph them, so I'll just kind of let you look and go through all those examples. But you get several different applications. You get a growth model application. There is economics and business, another application with average and marginal and fixed costs, variable costs. All of these are going to be using the same properties. So just look at those terms, and from here I'm going to go ahead and jump into number 1, which is just a definition. It just says explain the difference between the average rate of change and the instantaneous rate of change of a function of f. So the average is just the velocity, instantaneous is going to be the limit. So the instantaneous rate of change is where the average rate of change is the limit as x goes to 0. No, so the instantaneous rate of change is when we take the limit. This would be the average. Average rate of change is here. We're missing the denominator. Instantaneous rate of change, nope. Okay, D, the average rate of change, this function, whereas the instantaneous rate of change is the limit as x goes to 0. Okay, so D is going to be the one that matches the definition that we just went over in the text.